Let me share something fascinating right at the start. We are extraordinarily lucky to exist in this particular sliver of cosmic time. Stars are still burning out there, billions of them, and that simple fact makes us almost cosmically privileged. Because when you zoom out and look at the full sweep of universal history, the era of starlight turns out to be a brief, shining exception in an otherwise endless darkness. Almost everything that will ever happen to this universe will happen in the cold and the black, long after the last sun has gone quiet. So what does the death of the universe actually look like? That's what I've spent decades trying to understand, and what I want to walk you through right now. Settle in, because this is going to be quite a ride. Here's where we start. Roughly 100 trillion years from now, the final star will exhaust the last of its hydrogen fuel. It'll collapse inward, shrinking into a white dwarf, a dense, dimly glowing ember that will slowly bleed away its remaining warmth into the void. Eventually, it too will go dark, becoming what astronomers call a black dwarf. At that point, the stellar era ends. And just to give you a sense of scale, those 100 trillion years represent roughly 10,000 times the current age of the universe. Starlight, in other words, has a good long run ahead of it. But in the grand accounting of cosmic time, even that run is just an opening act. You know what's interesting? Even after every single star is extinguished, the universe won't have experienced anything close to true old age. The epochs that follow will make the stellar era look like a Tuesday morning. The universe will spend the overwhelming majority of its existence, essentially all of it, in a state of accelerating darkness, inching toward maximum entropy, toward what physicists call heat death. But don't mistake that slow march for uneventfulness. There are still mechanisms at work, processes that will gradually transform what's left into something far less interesting in the technical thermodynamic sense. The universe cools, energy disperses, entropy climbs. Now, could civilization survive all this? Possibly. A sufficiently advanced civilization might learn to harness the very processes of cosmic decay, riding them like a wave rather than being crushed by them. Life and structure can persist as long as the universe remains out of perfect equilibrium. That equilibrium, heat death, is the finish line. Our goal today is to figure out two things. How long does it take to reach that finish line, and what are the specific milestones along the way? Scientists and science fiction writers have sketched out all kinds of endpoints for our civilization. Earth destroyed by asteroid impact. The sun expanding into a red giant, swallowing our planet. The Andromeda galaxy, currently about 2.5 million light-years away, slamming into the Milky Way. Eventually, that last scenario plays out. Our galaxy merges with Andromeda, and the resulting structure is composed almost entirely of stellar corpses, neutron stars, black holes left behind by massive stars, and white dwarfs shed by smaller ones. Those white dwarfs, as I mentioned, will eventually cool into black dwarfs. That cooling process takes a few billion years. Fast compared to how long the stars themselves burn, but still an immense stretch of time on any human scale. And all the while, a serious question looms over whatever remains of life. Where do you get your energy? Civilizations that survive into the red dwarf era, the long, slow twilight dominated by the universe's smallest, coolest stars, will have to fundamentally rethink their relationship with energy. Their connection to the broader cosmos will be severed long before that era ends. I've spent decades studying this, and one of the most striking things about the far future is what expansion does to the observable universe. The accelerating expansion of space means that galaxies are being pushed apart faster and faster. Eventually, galaxies beyond our local group will recede past what's called the cosmic event horizon, a boundary beyond which their light can never reach us, no matter how long we wait. By the time the red dwarf era kicks into full gear, even the cosmic microwave background radiation, the afterglow of the Big Bang itself, will have red-shifted into undetectability. Future civilizations will look out and see only their own galaxy, every piece of evidence that a Big Bang ever happened will have vanished from view. All right, the stellar era is over. What's next? We enter what I call the degenerate era, an age of decay. What's left in the universe at this point? Compact, ultra-dense objects, neutron stars, black holes, and those black dwarfs, the cooled-down remnants of former white dwarfs. From a quantum mechanical standpoint, these objects are packed to their limits. Every available quantum state is filled. The only way to compress them further is to cross the threshold into black hole territory. Interestingly, many of these black dwarfs may still have planetary systems orbiting them, remnants from their stellar youth. Imagining civilizations clinging to existence on pitch-black worlds around cold stellar corpses stretches the imagination, but it's not ruled out by physics. However, even those worlds are living on borrowed time. Here's what brings them down: gravitational encounters. As stellar remnants drift through the galaxy, they occasionally pass close to one another. These near misses tug at the planets in orbit, slowly ejecting them or pulling them in. Over a time scale of roughly 1,000 trillion years, that's 10 to the 15th power, essentially every planetary system in every galaxy will be disrupted. Planets flung into the void, or spiraling into the dense stellar remnants they once called home. And then there's the ultimate fate of the galaxies themselves. Gravitational dynamics within the merged Milky Way Andromeda system and in galaxies everywhere will continue operating even after starlight is gone. The lighter remnants, mostly black dwarfs plus frozen planets and asteroids, will gradually be flung out of the galaxy entirely. The heavier bodies, neutron stars, black holes, will sink toward the center. According to calculations by Freeman Dyson, somewhere between 90 and 99% of all stellar remnants in our galaxy will be ejected over approximately 10 to the 18th power years. By that point, the universe is 1,000,000 times older than it was when the last star died. Give it another factor of 10, and whatever's left in the galactic core will either collide with something or be swallowed into a supermassive black hole sitting at the center. And that brings us to one of the biggest unresolved questions in physics. Do protons decay? Let me explain why that matters. Protons are the most stable composite particles we know of. According to the standard model of particle physics, they should last forever. But certain theoretical extensions of the standard model, grand unified theories, predict that protons can eventually decay, converting into positrons, neutrinos, and gamma-ray photons. We've never observed this happening. Enormous underground detectors filled with water have been watching for decades, and so far nothing. That non-observation tells us that if protons do decay, their half-life must be at least 10 to the 34th power years. If proton decay is real, then somewhere between 10 to the 39th and 10 to the 40th power years from now, every proton in the observable universe will be gone. Planets, black dwarfs, cosmic dust, all of it dissolves into a thin soup of photons, leptons, and black holes. Welcome, ladies and gentlemen, to the black hole era. Now, black holes are fascinating objects, and not just because of their gravitational grip. They also radiate. Stephen Hawking showed that quantum mechanical effects cause black holes to slowly emit particles, mostly low-energy radiation, gradually losing mass over time. This process, known as Hawking radiation, is almost incomprehensibly slow for large black holes. A stellar mass black hole of about 10 solar masses needs roughly 10 to the 67th power years to fully evaporate. And the giants, the supermassive black holes that once anchored entire galaxies, potentially containing hundreds of trillions of solar masses, could persist for up to 10 to the 106th power years. That's 1,000,000 Google years. It's a number that doesn't fit inside a human brain, and I've tried. During the black hole era, a sufficiently advanced civilization could theoretically still extract usable energy. Black holes can function as exotic engines, through Hawking radiation at minimum, or through more elaborate mechanisms like the Penrose process, which extracts rotational energy from spinning black holes. If life finds a way to tap those sources, it buys itself an almost unimaginable extension of time. What about dark matter? By this point, it's almost certainly gone too, either annihilated through particle collisions or captured by dense stellar remnants earlier in the degenerate era and eventually swept up into black holes. Then comes the end of the black hole era itself. One by one, the last black holes flicker out in bursts of gamma radiation, brief, brilliant flashes that will light up the universe for the first time in countless eons. After those final explosions, what remains is an expanding, thinning fog of elementary particles and photons. No gravity to pull them together, no energy gradients to exploit. Just an ever more dilute mist spreading across an ever-expanding space. That's heat death. That's the terminus. But, and here's where I want to backtrack, I've been assuming protons do decay. What if they don't? This changes the timeline dramatically, though not the destination. Without proton decay, the denser stellar remnants remain intact far longer, but quantum mechanics doesn't let anything stay truly stable given enough time. A process called quantum tunneling, which lets particles cross energy barriers they classically shouldn't be able to cross, will slowly transform matter into its lowest possible energy state. Think of a marble rolling toward a hill it doesn't have enough energy to climb. Classical physics says it stops at the base. Quantum mechanics says there's a small but non-zero probability it passes through the hill as if it weren't there. Applied to matter on cosmic timescales, quantum tunneling means that elements lighter than iron will gradually fuse into heavier ones, while elements heavier than iron will decay toward it. Iron represents the bottom of the nuclear energy valley, the most stable nuclear configuration. So the end state, for all remaining matter, is perfect iron spheres. Former planets, former asteroids, former black dwarfs, all converted into giant iron balls over approximately 10 to the 1,500th power years. Even those iron spheres won't last forever. Quantum tunneling will also cause matter to migrate from the surface toward the core, gradually pushing these objects toward neutron star-like densities. That process takes on the order of 10 to the power of 10 to the 76th years. But here's a possible shortcut. If tiny black holes are physically possible, and Freeman Dyson noted that the minimum black hole mass might be the Planck mass, about 20 micrograms, then quantum tunneling could cause small nuclei within larger bodies to collapse into microscopic black holes, which then consume the surrounding matter. In that scenario, everything larger than a dust grain collapses into a black hole within 10 to the power of 10 to the 26th years, and then those black holes evaporate via Hawking radiation on the usual schedule. So whether protons decay or not, the destination is the same, a gradually dispersing haze of particles expanding through an accelerating universe incapable of supporting any structure or process that could harness energy. The timeline differs. 1 million Google years if protons decay, something far more extreme if they don't, but the endpoint is identical, heat death. Now I'd be doing you a disservice if I didn't mention a few alternatives, not scientific predictions, but genuine physical possibilities that some researchers find worth considering. First, dark energy might not be constant. If its strength grows over time, it could eventually become powerful enough to tear apart galaxies, then solar systems, then planets, then atoms themselves, a scenario called the Big Rip, a violent counterpart to the slow fade of heat death. Second, quantum fluctuations in a sufficiently old universe might spontaneously nucleate entirely new universes in small pockets of space, each beginning its own Big Bang. Third, if gravity somehow overcomes dark energy in isolated regions, those regions could collapse back into singularities and re-expand, essentially running local versions of the Big Bang with lower initial energy, a kind of cosmic recycling. These aren't hypotheses in the strict scientific sense, they can't be tested, but they're not mere fantasy either. They emerge from legitimate physical frameworks. I leave them to the theorists and science fiction writers who are equally qualified to explore them. What we can say with confidence is this: the death of the universe will arrive somewhere between 1,000,000 Google years and 10 to the power of 10 to the 50th years from now, numbers so large they're essentially meaningless to intuition, but not to mathematics. And the physics that governs those final eons we've actually made serious progress in describing. We exist in the bright, warm, star-filled opening pages of a story that will run for an almost incomprehensible length of time. Most of that story will be dark and cold and quiet, but here we are in the lucky chapter, asking questions about the ending. I've spent my entire career on questions like this one, and I still find it breathtaking. The universe will die, but understanding how it dies tells us something profound about what it is right now and what it means that we're here to watch.